structural plate solutions presented by Contech. Before we start today's presentation, we would like to cover a few housekeeping matters that will ensure we have a smooth presentation. We have placed all phones on mute to cut down on background noise and to ensure everyone can hear the presentation. At the conclusion of today's webinar, we will provide information on how to obtain PDH certificates for today's presentation. The webinar is scheduled to last for 1 hour. We will have about 50 minutes of presentation followed by a question and answer period. When you logged on to the webinar, the GoToWebinar window will have appeared on the upper right-hand corner of your screen. This window will minimize by itself after a few seconds so that it does not interfere with you viewing the webinar. If you would like to maximize this window, just click on the small red arrow and the window will be maximized. The blue box in the GoToWebinar window will allow you to minimize or maximize the presentation, so you can view it in whatever size works best for you. If you have a question, please type your question into the question box. We will be taking questions throughout the webinar. Presenting today will be Brian Flint and Bob Moore from Contech. Brian Flint is the plate product manager from Contech. He has been with Contech for over 27 years in numerous sales and marketing roles, focusing on corrugated metal structures. Bob Moore is a region engineer for Contech. He has more than 20 years of manufacturing, sales, and marketing experience with the company. Our guest speaker will be Mitch Hardert, Vice President and Chief Engineer for CBC Engineers. Mitch has more than 18 years of experience focused on geotechnical engineering investigations and buried bridge structure design, evaluation, remediation, and load rating. He is a registered professional engineer in 48 states. Now I would like to turn the presentation over to Mitch.
Thank you, Lisa. Appreciate the opportunity to speak to everyone. My name is Mitch Hardert. I am with CBC Engineers. Our office is located in Centerville, Ohio, near Dayton, Ohio. Today I'm going to be speaking with you for my short portion of the presentation about load rating, specifically about load rating of buried flexible structures. First, we have to ask, why do we load rate structures? At the end of the day, it's a public safety issue. We as consultants and agencies need to know and have a numerical way of verifying that our crossing structures have sufficient capacity to carry the loads they're being asked to carry. Most of the structures that are load rated today in a conventional sense are conventional bridges. Those are generally have spans of 20 feet or more as mandated by FHWA. We here in Ohio go down to 10-foot span as bridges. Today, more and more DOTs, states, and municipalities are being pressured and mandated by FHWA to look at smaller diameter structures and load rate those as well. And that's what we'll be speaking about today. This is a snapshot of the front page of a document that was developed by the NCSPA going on about 20 years ago now with the help of Professor Duncan. This is an implementation of the general load rating procedure as presented in the what's now called the Manual of Bridge Evaluation by AASHTO. And this document is an LFD implementation of that load rating process. We'll talk about this document a little more later on. I would draw your attention to the part in red in that document where it talks about that structures, flexible buried structures, to do an accurate load rating, you must know the in-service or in-situ shape and condition of that structure to do an accurate load rating. Just some general information about loading on flexible buried structures. Generally, there's two categories of flexible buried structures: ring compression structures that develop their load carrying capability by carrying thrust tangent to the pipe wall. There's also flexural-based structures such as aluminum box culverts that depend on their moment capacity of the plate to carry the load. For ring compression structures, which we'll more focus on today, pretty simple calculation of the ring compression or thrust load in the pipe wall based on the pressure at the crown of the structure and the span of the structure. That pressure at the crown of the structure generally is comprised of two components. One is your permanent earth loads or dead loads. Could also be pavement loads or concrete slab loads if you have a load relief slab of some kind over the arch. Second component is the temporary live load over the structure. This can be vehicles or tractor trailers or railroad or even airplanes. Flexible buried structures are inherently part of a soil structure interaction system, meaning they partially depend on their stability is dependent on the stiffness of the backfill material and the in situ embankment fill around the structure. If a structure is looked at and it's seen to have excessive shape change, a likely culprit of excessive shape change of a flexible buried structure is insufficient backfill support. This is a retro looking figure, but it speaks well to this idea of how backfill competency and consistency plays a major role in the expected shape change of a flexible structure. If you look at that plot, down at the bottom of the plot, the lines there are representative of a more granular, higher friction angle, higher quality type backfill materials. As you work up the chart, you see lines that represent more cohesive, finer grain materials that would have a higher propensity for consolidation or displacement. And you can see as you work from right to left on the chart, as you go from a higher degree of compaction to a lower degree of compaction, the expected movement, the expected shape change of that structure increases. As we spoke about relative to doing load ratings, you must know the existing structure geometry to be able to load rate a buried flexible structure. The Ohio DOT and other state agencies have developed relatively in-depth procedures for doing field evaluations of in situ flexible structures. Part of this is to determine the shape of the structure as well as to assess the overall condition of that structure, which could contribute to varied capacities in the load rating calculations. Flexible buried structures are designed to deflect, designed to change shape. As a flexible structure deflects under earth load, there is a soil arching that is created that inherently increases the overall load carrying capacity of the entire system. As we spoke about, if the backfill support is insufficient, there is the possibility of excessive shape change that could result in lowered capacity and or higher loading on that structure. That needs to be considered in a load rating. Another possibility of a cause of shape change in a structure is excessive live load with insufficient cover on a structure. A lot of times this happens during construction where there is insufficient cover over a structure. During construction, a large piece of construction equipment is run over it, and you see a localized deflection of the structure where that concentrated loading was applied, signifying that the overall flexural capacity of that structure in its top arc has been exceeded. The load rating of a structure, of a flexible structure, needs to be based on the critical shape geometry in any area that could be traversed by live loads. One generally accepted way of measuring shape change for flexible structures is to determine a series of chord and mid-ordinates to the interior wall of the structure. Most ring compression structures are composed of a series of arcs that can be defined by chords and mid-ordinates. This you see on your screen is that for a round structure. Similar type setup for a pipe arch structure or an elliptical structure or an underpass type structure. Those measurements can be, where physically possible to do so, can be manually measured by using 4-foot levels, measuring rods, architect's rule or engineer's rule to measure those distances. A lot of cases, especially when you get into larger diameter structures or you get into difficult site conditions, you need to be a little more innovative about how to get those measurements. We as a consultant try to be creative in that. We've developed some, patented some rudimentary type procedures to do that. This one on your screen is simple but effective. It consists of a handheld laser measuring device mounted to a tripod that has a rotating wheel on it that is able to be rotated at an even degree increment radially. And at each degree increment, you're able to make a laser measurement out to the interior wall of a pipe, and can basically make the spokes of a wheel that measure out to the pipe wall around a full 360 degrees. Based on those kind of measurements, that data can be plugged into some CAD software, and you can get a relatively accurate, relatively exact, I'd go to say, representation of the interior geometry of a structure at whatever station you want to measure it at. From there, that information can be used to physically measure those chords and mid-ordinates within the CAD software, or you can measure the radii of certain arcs. You can also, if the decision is made that some kind of remedial measures for a structure are needed, you've already got plots available to you that would show the size of a reline pipe that could fit, or even if there's going to be stiffeners of some type added, you've got the geometry of the structure there ready to use. Another relatively simple but very effective piece of software is called Multispan. It is essentially a geometry comparison model. It allows a direct input of these measured chord and mid-ordinate values for a certain pipe at certain stations, and you're able to measure or compare those measured values with theoretical values for that certain shape, or you can put in measurements from successive sets of measurements and determine a rate of deflection, or if there is any continued deflection in a structure over time. The software will also determine the top radius of a structure that is then directly an input into the load rating calculation. It also computes other factors, as you see in that list, and also gives guidance recommendations. I would not say these are cut in stone recommendations, but they are guidance recommendations based on the evaluation of many in-place structures. This is an example table of some of the mid-ordinate output from Multispan. Not a complex thing, but it's very effective to show you where you're seeing deflection and not. You'll see that it generally concentrates on the top center, top left, top right mid-ordinates. The top arc of a structure is generally its main load-carrying component, so that's what's focused on. Here's the general guidance recommendations from Multispan. You see as the level of mid-ordinate change or shortening occurs, along with the depth of cover that you're looking at, the guidance recommendation becomes more severe. Once you reach that 25 to 30% mid-ordinate change based on field evaluation of in-place structures, you've reached a level of deflection where the structure may no longer be acting like a ring compression structure. The radius may be so flat that it's starting to act like a flexure or beam type structure. So once you've made the measurements of the structure, you've got the plots done, a little more data is needed to be able to actually do the load rating, some more field observations. Some of those specific to flexible buried structures are what you see here. Some of these will directly affect the load rating, such as features that are causing a loss in section, or deflections that are causing that top radius to increase, or features that are causing the load in the pipe wall to be increased. Others are just ones that are monitored on a continuous basis to verify if any conditions are continuing to deteriorate, or if further, more in-depth evaluation than a simple visual inspection is necessary. Again, those are some of those same repeated. These are very specific to buried flexible structures. Once you've got this data along with the shape measurements, you're able to do the Multispan analysis like we talked about. You're also able to do a conventional NBIS type observation rating on a structure, as well as move on to the actual empirical load rating. Many of you may be familiar with the NBIS rating for conventional bridges. This is a system that was developed in conjunction with ODOT and FHWA by a former colleague of mine that is still used today for rating, observation rating of flexible buried structures. It's got some categories that are specific to those types of structures. It's got 0 to 6 kind of rating categories. This is a general comparison of that type system with the conventional MBIS system. If you've got no category less than 3 or 3 or less, you're generally in that A, uniform deterioration type category. If you've got a single category that is got a score of 3 or less, you move over into the B type, more localized deterioration, and which is similar to how the MBIS overall rating is determined. So what is a load rating? Again, we talked about we've got a capacity of an element based on its in situ conditions, and we've got permanent dead loads on there that take away a percentage of that capacity, and we're left with some net capacity of that element, whatever the critical element is in a structure. And we're using a numerical procedure to verify that that net capacity is enough to safely carry the loading from a particular vehicle on that structure. This type of load rating is empirical, it is numerical, it is different than an inspection type rating, which has some subjectivity to it. What would cause you to do a load rating on an existing structure that may have been previously load rated? Similar to this list is similar for conventional bridges. Anything that has changed the physical conditions, such as alterations being, was there some type of slab placed over the structure? Was the height of cover changed? Was there some type of deflection? Was the structure impacted, being an underpass type structure maybe, and it changed the geometry? Was there some type of stiffener or some type of new component added to the structure? The others are similar things that you find in those observations as to was there a physical change in the structure that would make the existing load rating no longer applicable. There's generally 3 types of load rating methods. 2 of these are about the only ones used anymore. We got working stress or ASR kind of rating. That's probably the most conservative. It's not generally used much anymore. LFR and LRFR are the more common ones today. LFR used to be the more common one. It seems that the shift is being made to LRFR in response to the way all design is moving to LRFD. You can see when we talk about buried flexible structures, these product lines have been around for a long time in some instances. You've got General CMP, which is well over 100 years old, and steel structural plate, which is that SSP is going on 80, 90 years there. And the others, the aluminum type structures, are not as old, but they have been around before LRFD was ever even a thought. So it has to be discussed, and each state generally has protocols for, depending on when a structure was designed and what code it was designed under, as to which rating method should be used. In a load rating, there's 2 different rating levels: an inventory rating, which is a rating that's done for routine, repetitive type vehicles, your design type vehicles. Under LFR, you'd be an HS20 type vehicle. Under LRFR, you'd be an HL93 with a truck or a tandem and your lane loading. Operating stress is more of your non-routine, non-repetitive vehicles, generally like your legal loads, AASHTO legal loads, or your posting loads. These are loads or vehicles that if they were on a routine basis, they would likely result in a reduced service life for that structure. I would say that some of these slides you'll see in a minute will have come from an ODOT previous presentation. These are the Ohio vehicles. Bus being an Ohio firm, we deal with Ohio load ratings a lot. These are the ones that are generally for an LFR rating. These are the ones that are generally looked at. You've got your normal design vehicle there under both inventory and operating, and as well as your more legal, AASHTO legal type loads in the 2F1 through 5C1 vehicles. These coming up are the diagrams, the loading and axle diagrams for those ODOT specific vehicles. A load rating is done for a specific vehicle. It is not some general rating that covers every single vehicle that could ever go over it. It is a rating specific for the vehicle being investigated. For that reason, it's critically vital for the axle configuration, the tire pattern, and the axle loading to be known for that vehicle. The calculations will be done, the pressures on the structure from that vehicle calculated based on those specific vehicle configurations. There's HS20 and the 2F1. These kind of get more severe as you go further through. Like in a 5C1 vehicle, you've got axles at 4 feet on center. Depending on a height of cover, you will likely have superposition of axle loading on a structure from 2 different axles that will greatly increase the pressure on the crown of that structure for that type of vehicle. This is our basic load rating equation, like you would see out of the MBE or other load rating documentation. You've got a capacity of a certain element. That capacity could either be based on yield. In a case of buried flexible structures, you either got wall stress or buckling. Both of those capacities are based on yield. You've got seam strength, which is based on an ultimate capacity. And then at some lower heights of cover, you've also got minimum cover or moment type capacity, which is based on plastic moment capacity. Again, based on whether you're doing LFR or LRFR, you're putting factors on the dead load and the live load, maybe the capacity. Like I said, LFR and LRFR tend to give higher rating factors than a WSR or allowable stress design. Taking a little closer look at this NCSPA Design Data Sheet 19, this document is available on NCSPA website. I again draw your attention to that statement in red that you must know the in situ shape and condition of a buried flexible structure to do an accurate load rating. Unless you're doing a load rating on a design structure that is yet to be installed, you cannot do a desk rating on a flexible buried structure and it be accurate. Here's the general expanded load rating equation for buried flexible structures. Again, this is an LFR method, not LRFR. If you're doing LRFR, there's some other factors that would be included in this. You've got your 1.3 ash toe factor there, the overall culvert type factor, and then whether you're in a ring compression or a flexural base structure, you've got your beta load factor there. You can see that the inventory load rating factor is generally computed as 60% of the operating load rating factor, unless you have a minimum cover condition controlling that rating. This is the impact consideration for live load based out of standard ash toe spec. If you're doing LRFD or LRFR rating, there's a different consideration for impact, and it considers it to a deeper depth than just 3 feet as shown in this table. Here's the ash toe derived live load pressures at depth for H20, H25 vehicle. Again, this is a specific number for those types of vehicles. This is based on the standard ash toe distribution of load through the overburdened soil above the structure, which is based on a 0.875 to 1 load distribution. LRFR, LRFD has their own specific based on material type, either being 0.575 to 1 or 0.5 to 1. At the lower heights of cover, you can see the highly increased magnitude in those pressures due to that higher influence of impact. Here's the specific operating rating, load rating equation based on wall strength. You've got your capacity of the pipe wall T-cap there, which is again either based on wall strength or wall buckling or seam strength. You've got your earth load there, which is factored by a factor of 1.95. You can see in those two equations there that for a structure that has seen shape change, the rate that the measured top radius, the maximum measured top radius in a structure is substituted, twice that top radius is substituted for the span in the load rating calculations. You can see as a structure undergoes shape change, that directly influences the calculated dead load applied to the structure, as well as in the live load calculation, that span over 2 or that top radius is included with the live load plus impact. So deflection or shape change of a structure is directly influencing its load rating. Relative to the buckling strength, there's a provision for, based on the level of that shape change, level of deflection, that buckling strength is reduced. There's also a minimum height of cover component to the load rating, and it's the actual reported load rating is the minimum of based on wall strength or minimum cover. There are AASHTO defined minimum required covers for structures based on their span and different components. Then you have your actual height of cover in the numerator. That C factor is a reduction in the required factor of safety based on this being for operating load for non-routine vehicles. The inventory load rating factor, like I said, is generally computed as 60% of the wall area or wall strength based operating factor, or it's again based on minimum cover without the reduction C factor in factor of safety, based on this being for inventory or routine vehicle loads. Once the rating factors are computed, it's some states, depending on where you're analyzing it at and who for, some states just have you report the rating factors themselves. Other states require that the ratings be documented in a tonnage of a vehicle, which would be based on the gross vehicle weight and the computed rating factor. Like I mentioned, that each state is pretty unique in what vehicles they want to be load rated for, as well as how they want those ratings to be documented and on what kind of form they want them, format they want them presented in. In conclusion, just some things to remember. We talked about the age of some of these profiles, corrugation profiles that go back almost 100 years. Steel structural plate, which is a 6x2 corrugation today, was not always 6x2. It varied in corrugation pitch and depth. So if you're looking at older structures, you need to be sure you know the correct section properties. A critical part is about this top radius. Has to be measured, has to be physically known what that top radius is, and that is used, that maximum radius, twice that is used as the effective span of that structure in the load rating. We talked about the desire for flexible structures to change shape to increase their load carrying capability. We also talked about the idea of insufficient backfill support allowing excessive deflection to occur. This is all the more reason why monitoring in any prudent structure would need to be monitored, and these are no different. They need to be monitored. We also talked about how deflection or flattening of a curve, if it becomes 25 to 30%, that range or more, you've basically reached a point where that curvature is likely no longer acting like an arc and maybe acting like a flexural piece. The others there, I'll let you read those. They're pretty self-explanatory things we've talked about. I appreciate your time here today, and I'll pass it on.
Thanks, Mitch. We really appreciate your presentation. Ladies and gentlemen of the audience, we'd like to take some time and ask a poll question of you to get your feedback on the implementations for load rating programs. Are you being required to implement a load rating program for your area? Your choices are: my colleagues and I have not been asked to implement a program, my colleagues and I have been approached about implementing a program, and my colleagues and I plan to implement a program in the near future. Please go ahead and log in your votes. I'll leave the poll open for a few more seconds to make sure everybody gets a chance. I apologize in advance if you are on a mobile device, iPad, iPhone, or other mobile device. We cannot let you vote in the poll questions. It's just a little technology glitch right now. They're working on fixing it. So again, I apologize in advance. Also, we are taking questions throughout the entire presentation, so if you want to go ahead and log those in the little chat window on the right-hand side of your screen, we'll try to get to them at the end of the presentation. All right, I see that most people have voted, so I'm going to go ahead and close the results and share. 76% of you have not been asked to implement a program like this. 14% have been approached about it, and 9% plan to implement in the near future. Thank you again. We appreciate your feedback, and I will turn this over to Bob.
Hello, I'm Bob Moore. I've been with Contech for 24 years. I'm currently the region engineer for the North Central region located in Shakopee, Minnesota. I have a mechanical engineering degree from the University of Missouri at Rolla. For the next few minutes, I want to discuss some reasons why a design engineer would consider aluminum and steel structural plate, and then review 3 case history projects using aluminum and steel structural plate in hydraulic applications. The slide you're seeing now shows Contech's manufacturing capabilities for a full line of bridge and buried bridge products, including steel and aluminum structural plate, steel bridge core, concrete precast conspan, and BEBO, and our steel truss bridges. You'll hear the phrase buried bridge a few times in this presentation. That's just our definition of a culvert with a span of 20 foot or more. Why design with aluminum and steel structural plate? There are many advantages. One of the main advantages is the cost savings over traditional concrete small span bridges and large concrete culverts. Another large advantage is the speed of construction, including the speed of material delivery after an order placement, the speed of assembly and installation, which all help in reducing road close time. In addition, aluminum and steel have a very high recycled content. There are many different shapes you can choose from. Each shape may have a design advantage for your project. As an example, a round steel multiplate, 12 foot in diameter, can handle over 100 feet of fill. Box shapes and arch shapes on footings have hydraulic advantages, as you can see in the 2 photos on this slide. Structural plate products are designed to meet current AASHTO, LRFD loading, and other loading conditions, including railroad, special crane loading, and military loading applications. Contech is ready to assist you with any structural design needs you may have. We're having a little difficulty with forwarding these photos. This next slide shows a galvanized steel multiplate. This particular structure is 74 years old. With no bottom in it, because it's an arch, there's no waterside corrosion on this structure. And there's a picture of that steel multiplate arch. Today, we use a lot of aluminum structural plate. Here's a modern-day aluminum structural plate installed on footings after 5 years of service. You can see the hydraulic advantage for this 3-side arch culvert. In addition, aluminum head walls and wing walls provide economy versus cast-in-place concrete. This photo shows one of the steps in the hot dip galvanizing process of steel multiplate. Hot dip galvanizing is the process of applying zinc to bare steel. There are several other items to increase the durability of steel multiplate. Some of those items include backfilling with a clean, granular, well-drained material, installing a PVC membrane over the top of the structure to keep salts off the crown is a good practice, not only for steel plate design, but also for concrete design. Other ways to increase the durability are to design with an open bottom culvert. This older project shows the durability of aluminum structural plate pipe arch. After 46 years in service, this aluminum plate has no corrosion. You can see the photo to the right. That's the invert. There's no corrosion on that aluminum. This next photo is of a round aluminum structural plate in the Bay of Fundy in Maine. The aluminum plate is made of 50-52 marine-grade alloy. After 47 years in a saltwater environment, the plate is in excellent condition. Note the backfill was a clean granular material, allowing the aluminum to breathe and form a protective aluminum oxide barrier. Aluminum allows for a wider, more corrosive environment range than steel multiplate. Aluminum has been traditionally used in corrosive environments such as sea and brackish waters, as well as acidic environments such as cranberry bogs. The next few slides will focus on 3 different hydraulic applications with over a 20-foot span using both steel and aluminum structural plate. An express foundation is a precast foundation system that blends the speed of precast concrete with the economy of cast in place. Express foundations can be used on both steel and aluminum plate, as well as 3-side conspan concrete arch structures. The express foundations are pre-designed with rebar placed at the plant prior to shipping. The purpose of the express foundation is to speed the construction process. Just as they say at the Wisconsin DOT, every day counts. Express foundations are picked off the flatbed truck and placed on a level foundation. You can see riprap is placed on the inside of the footings before the structure is installed. There is no need to construct concrete forms, which can save several days in the construction process. The lightweight aluminum plate structure is lifted into place with 1 pick and 1 drop. This particular structure is a 22-foot, 9-inch span structure. These are quick and easy to install. The plate structure fits easily into the express foundation. The next step is to fill the void of the express foundation with concrete. You do not need to have experienced concrete laborers to do this job. This particular job was done by a county workforce. The next slide, you'll see the finished buried bridge with aluminum head walls and wing walls. This head wall system is a tieback system that requires no concrete, which saves time. The entire project took approximately 7 working days from start to finish. And approximately 3 weeks of construction time was saved going from cast-in-place footings and cast-in-place head walls to the express foundations and aluminum head walls and wing walls. This is the same project 1 year later. Notice there is no bridge deck to maintain. It's a smooth surface throughout the road and over the culvert structure. This is a 33-foot span aluminum box culvert shape. This structure was assembled in the parking lot adjacent to the project site. The entire 33-foot span structure was lifted and set into place in one piece. The express foundation was lifted off the truck and installed on a level ground. Concrete was then poured in the void space, as seen in the photo on the right. These photos show the before and after pouring the concrete into the express foundation. The contractor on this project was a utility contractor who does not specialize in the forming and pouring of concrete. The express foundations gave him more confidence to build the job. This is the finished photo of the buried bridge, complete with aluminum head walls and aluminum wing walls. Once again, there is no bridge deck to maintain. This is an Iowa Department of Transportation project showing the before and after photos of a 50-foot span concrete beam bridge that needed to be replaced. The Department of Transportation considered 3 different options for bridge replacement. 2 of those options were conventional bridges, and the third was a 33-foot span horizontal ellipse steel multiplate. These photos show construction of the new steel multiplate during the entire construction process. There was no road close time during this entire construction. There are many Amish people driving horse and buggy in this part of the county. There would have been several miles of detour if a traditional bridge construction was chosen. This next slide shows a page from the plan set. Standard aggregate backfill was used around most of the structure, while flowable fill was used in between the crown of the structure and the bottom of the bridge deck. This photo is during the construction process. You'll see that concrete toe walls were poured to prevent undermining of the structure. The bridge deck was left in place. Holes were core drilled from the top of the bridge deck in between the I-beams. Then they were filled with a flowable fill material. Leaving the bridge deck in place saved both time and money for the owner. By eliminating a conventional concrete beam bridge and replacing with a 33-foot span steel multiplate, the owner was able to eliminate the bridge deck. No bridge deck means no bridge deck maintenance, no bump on, bump off the bridge, no freezing of the bridge deck, a much wider shoulder to drive on, and ultimately a safer road to drive on. Thanks for listening to this portion of the webinar. After another poll question, Brian Flint will discuss the bridge core product, which has a 15-inch span by 5.5-inch deep corrugation, allowing for larger spans in the standard multiplate as seen in this photo.
Thanks, Bob. Ladies and gentlemen, as Bob stated, we do have another poll question. What is the biggest benefit you see in utilizing metal structures? Is it the speed of construction? Is it to utilize your own workforce? Is it the ease of design? Or is it minimize disruption to the general public? Please go ahead and log your votes now. We'd love to know what you think is the biggest benefit. Again, we are still taking questions, so please don't forget to log them in at the bottom of your screen. We'd be happy to answer them. If we don't get to your question on the live webinar today, we will have someone follow up with you shortly. So please go ahead and ask any questions you have. I'll leave the poll open for a few more seconds to make sure everyone gets a chance to vote. Okay, I'm going to go ahead and close the poll. 61% of you had said the speed of construction was the biggest benefit. 28% said minimize disruption to the general public. 10% said ease of design, and 2% said utilize your own workforce. Thank you very much for your participation, and I will go ahead and turn the presentation back over to Brian Flint.
Thanks, Lisa. I appreciate it. Bob did a nice job of outlining many of the features of our aluminum structural plate and our multi-plate product line. The chart here shows the 3 corrugation Contech provides in structural plate today. Our 6-inch by 2-inch corrugation for our steel multi-plate product line, our 9 by 2.5 corrugation for our aluminum structural plate product line, and in the center there, our 15-inch by 5.5-inch deep corrugated or bridge core product line that I'm going to discuss this afternoon. As a little background, corrugated metal pipes started almost 120 years ago. Initially, they used a shallow depth, 1/2-inch deep corrugated product that were rolled into cans, and then individual rivets were placed to hold the cans together. Then they completed a complete pipe section. Once that pipe section was done, it was shipped to a job site and then installed by the contractor. As the need for larger pipes grew, the riveted pipes had limits in its shipping and also difficulty in handling with the contractor during the installation process. In the 1930s, Armco Contech developed our multi-plate product line, our 6-inch by 2-inch line. 6-inch by 2-inch multi-plate is an alternative to conventional bridge systems. It does give owners economy and speed in the bridge construction process. The use of corrugated plates shipped and assembled on site allows engineers to take advantage of corrugated structures for much larger applications, a key point in our success. But as time went on, we developed superspans. The need to get larger and bigger continued. The design of the culverts, we grew to safely do approximately 40 to 50-foot spans. Now we have bridge core. The 15-inch by 5-inch corrugation takes advantage of the multiplate concept and now allows for corrugated spans up to 65 feet. This deep corrugation provides a structure stiffness 9 times greater than conventional multiplate, a point we want to drive home today. This concept of pipe stiffness is an important point in CMP design. As you can see here, with all corrugated structures, pipe stiffness or pipe flexibility is a key factor in CMP design and installation. We find in many applications the pipe stiffness will control the design of the overall system from the start. So let's look at the flexibility factor formula that we have here today. The pipe diameter, or D, or span of the structure, the modulus of elasticity of the steel, or E, the moment of inertia, I, of the CSP section for a given gauge and corrugation is shown in the chart below. So as you remember in your math classes in school, with the I value in this formula in the denominator, the larger the I value, the smaller the flexible factor, and that's what we're trying to achieve. ASTRO specifications have set flexibility factors for specific structure shapes. Using these values, the calculated flexibility factor cannot exceed this set number. So therefore, for a given diameter, you can control the design by choosing the appropriate moment of inertia for a corrugation and gauge. This additional stiffness provided by the 15 by 5.5 corrugation helps control the overall shape of the flexible structure during assembly and installation. In this chart below, if you look at the rows of the 6-inch by 15.5-inch corrugation, those moment of inertias, you'll see the difference between the values is approximately 9 times. The 15 by 5.5 has 9 times the moment of inertia, therefore it correlates directly back to the flexibility factor as 9 times stiffer than 6 by 2 material. This is a key point in the installation of this type of a flexible structure. Since the 1970s, Armco and Contech have been promoting multiplate superspan with the conventional 6 by 2 corrugation for larger spans. Those spans typically over 26 foot. So over the years, we've manufactured thousands of structures in that 40 to 50 foot range maximum span. Each one of these structures requires a select backfill, an A1A, a very defined backfill material to allow you to get the type of support you need for this type of flexible structure. They require an on-site monitor person during the backfill process all the way through to minimum cover. And they require an installation of a reinforced concrete truss beam at the 10 and 2 o'clock position to be able to lock in that top arch. With the added stiffness provided by the deeper corrugation bridge core, we have some changes in how we're assembling these types of structures. They allow for a wider range of locally available backfill materials, a key point in the installation. Depending on the size, potentially require less structural monitoring during the installation process. They eliminate the need for the thrust beam in the structure design, which helps speed up the overall culvert installation. And in many cases, we can reduce the gauge for a given span to help with the overall bridge economy. Trying to optimize that shape, gauge, and span can really help us with bridge growth. We offer a variety of shapes and sizes with our bridge core product line. When larger spans are required, the deeper corrugation bridge core gives designers a lot more options in the shape selection. When possible, round structures are always the first choice. Round structures eliminate the cost and time of footing construction. They're the easiest to assemble, and they're also the most stable during the backfill process. When working in environmentally sensitive areas, the single radius and 2 radius arches can clear span restricted stream crossings, which is an important point in permitting today. This helps up the permitting process and to eliminate some key durability issues in our design. The bridge core box culverts can provide large spans and applications where you have limited elevation change between the invert and the top of the grade. When designing with decorrugated structures, AASHTO Section 12 of the Design Code gives very specific guidelines on how to evaluate these designs. AASHTO Section 12.8.9.3.2, that's a lot, states that the designer must use a accepted finite element analysis program to design these structures. In addition, the specification states we really need to understand the bridge location, the environment of that location, the in situ soils. We need to consider the strength and the stiffness of the corrugated steel material being utilized for this bridge. We can help with this process. With a proper geotech report based on the specific bridge location, we can start the finite element analysis for you. Information from the geotech report will help choose the structure shape, the structure's gauge, and if required, the potential footing size of this particular bridge. Once we have this information, then we can provide a material estimate for your budget. In addition, the AASHTO specification also requires the manufacturer to help facilitate an on-site pre-construction meeting to review the bridge core installation process, an important part of the overall bridge installation. In addition, at this time, we can outline the proper method for monitoring the structure during the backfill placement so that the manufacturer, the contractor, the engineer, and the owner are all on the exact same page. So no matter if you're considering a multi-plate, an aluminum structural plate, a super span, or a bridge core for your project, we have some tools that can be helpful to use along the way. To help you begin the structure selection process, we have compiled a structural plate design guide booklet for you to use. This design guide helps with the shape, sizes, and gauges for all of our plate structures. In addition, the structural plate design guide will give you some key help with proper specifications for your project. You can download this booklet from our website at www.conteches.com. Or for a hard copy, you can contact a Contech sales or bridge consultant near you. It's an awfully good book you should have in your library. Aluminum box culverts are used for bridge structures in all of our markets for a variety of different applications. If you're considering an aluminum box culvert for your project, log on to our website and use our own Design Your Own Bridge link for help. This link will utilize the aluminum box culvert Design Your Own Bridge tool to help you develop an initial proposal drawing and receive a material estimate for your specific bridge location. This tool gives you a real good look at what your bridge will look like from the initial design. Once you log on and you input some basic parameters that are key to the specific bridge that you're looking at, Contech will then email back to you a cross-section of that bridge, profile, plan view, and along with some key specification information for you to use as your initial proposal drawing. So log on today with this and check this out. It's an extremely useful tool, an aluminum box culvert bridge design. It's a lot of fun to get on and do. So as I wind down the presentation for today, I want to take you through a few case histories of some successful bridge core installations we've had so far. This 32-foot span, 2-radius arch bridge core was used in a housing development in Connecticut. This open-bottom bridge core structure provided the clearance required in an environmentally sensitive stream. The large span kept the normal water flow away from the structure and protected the overall stream during its construction process. In addition, the developer selected a modular block headwall to improve the important overall bridge aesthetics. Nice looking bridge. In another environmental application, this bridge core was used as a streetcar crossing in Elk City, Idaho, up in the middle of nowhere. The 46-foot 9-span bridge core single radius arch opened up 60,000 acres of watershed to help with future fish migration. In addition, the bridge core provided an economical solution for the United States Forest Service on this important Indian reservation. The project engineer here utilized projecting ends as a selected end treatment for this particular structure. Bridge core has been the product of choice in many mining applications across the country. In this important mining application, the bridge core is being used as fall protection for vehicles in this high wall location. The need for debris to be deflected away from traffic and people is key to mine safety here. This application is the right choice for the stiffer, deep corrugated bridge core structural plate. The Gateway Industrial Park in Gainesville, Georgia required a stream enclosure to open up this development. This 36-foot span bridge core was designed to handle over 25 foot of cover during heavy construction loads under minimum cover. The structure was constructed with a flexible wire-faced wall that was vegetated to provide a green end treatment solution, very popular today. A flexible wall with a flexible structure makes a lot of sense. In another mine application, this county road needed to cross this spur track to give rail access to a mine in Arizona. The 40-foot bridge core single radius arch provided the required track clearance and eliminated an unwanted at-grade crossing. The structure skew required a reinforced concrete head wall in conjunction with the modular block wing walls. This end treatment selection helped stabilize the structure during the backfill process. This environmentally sensitive project for the NRCS in New Hampshire needed help to support a damaged sanitary sewer line. The bridge core structure was installed to help protect the stream and provide the proper support for this pipe installation. The 32-foot single radius arch bridge core was built using an aluminum structural plate head wall, and then on the other end, the step level with concrete slope collars as its slope protection. Nice looking landscaping there. So that concludes our presentation for today. I truly appreciate everybody taking the time to visit with us and to sit in with our presentation. We hope that it was very helpful for you. If you have any questions, do not hesitate to contact anybody at Contech or CBC. We'd be glad to help you. And I'll turn this back to Lisa. Thank you very much.
Thanks, Brian. We do have a few more minutes. I think we could get maybe 2 questions in. Brian, this one came in as you were talking. Can you use an express foundation on a bridge core?
Yes, Lisa, you can. You can use an express foundation for any of our Contech bridge products. Bridge core, structural plate, the Multispan O series, along with even abutments for our truss bridges. Good question.
Great, thank you. And Mitch, can you help me out here? I did get one during your presentation. Can you help us to set up a load rating program for our county? Didn't specify the county.
Yes, thank you. Most definitely. In past instances similar to that, we've helped out in a variety of different levels of involvement. Some instances we've been asked to completely do all the field work and all the work necessary to do the load rating. Other instances asked to teach or instruct local workforce on how to do the field work, and we the office engineering. Other instances we've helped train in-house engineers on how to do the load rating process. We'd be more than happy to help anybody that needs it in any way we can.
Great, thanks, Mitch. And ladies and gentlemen, in an effort to save time, we're going to take as many questions as you can log in the next 2 minutes. Somebody will follow up with you. But there have been a few questions come up regarding the PDH certificates. At the close of the presentation, a new browser window should pop up on your screen with a survey about today's webinar. After you submit the survey, your responses will be manually processed, and you should receive a thank you for attending email within 24 hours. That will have a link to download your PDH credits. Again, this process is manual, so please be aware this will not be immediately following the presentation. If you have any other questions or if you have not received your email within 24 hours, please contact info@contechES.com. We thank you for your time and hope you learned something from our webinar today. Have a great rest of your day. Thank you again.
Thank you very much. Goodbye.